Let us take on another 60 multiple choice problems. This will constitute CSEC multiple choice practice paper 6. As usual, we will divide the entire practice paper into 4 sections of equal number of problems. Therefore, we will begin with 6A, which will be the first 15 problems. There we have 2 mixed numbers, and we are required to find their sum. The first thing that is worthy of note is that the fractions do not have the same denominator. In order to add them, we will have to find a common denominator. In this particular case, the LCM of the denominators. It is difficult to forget the whole number because it is present in every single option. Notice that we have the whole number here, so we will not forget that we have whole numbers as a part of each addend. The whole numbers must be added, and 5 plus 4 is equal to 9. The principles to be applied will be the same as mentioned before, namely, find the LCM of the denominators, that is, the minimum expression that each of them can divide into without leaving a remainder. And that number is 35. That will be our common denominator. 5 into 35 is 7, and then 7 multiplied by 2 is 14. So we say 5 into 35 is 7. 7 multiplied by 2 is 14. Then we come here and we say 7 into 35 is 5, and 5 multiplied by 3 is 15. Find the sum of the numerators. So 14 plus 15 is equal to 29. So we have 29 over 35. Do not forget that we have the sum of the whole numbers right there. The correct answer is option D. On the next slide, we will place some of the arithmetic operations under the microscope. Finding the LCM of 5 and 7 is pretty straightforward. It is as simple as multiplying both numbers together. However, let us take a look at how this may be done in order to convince ourselves that using a known method, the answer will still be correct. Let us use repeated division in a table, and that is the one that we always use. As a matter of fact, there are other methods that we may use, but this is the one of choice. Find the smallest prime number that can divide into 5 or 7. It turns out to be 5. So the smallest prime number that can divide into any of these will be 5. There we have our 5. 5 cannot divide into 7, so it returns unaffected to the next row. That is, 5 cannot divide into 7 without leaving a remainder. We are interested in numbers that will not give a remainder when we divide. So 5 into 7 will not leave a remainder, 7 returns. Then we say 5 into 5 is 1. One column is already exhausted. Find the smallest prime number that can divide into 7. It turns out to be 7. So after exhausting one of the numbers, we may move merrily on to the other. And the only prime number that can divide into any one of these, which is of course 7, and that number is 7. So 7 into 7 is 1, and the first one was already exhausted. Now both columns have already reached exhaustion. We will find the LCM of the expression by multiplying all of the factors. We only have 2 in this case. So 7 multiplied by 5 is 35. And we have found our LCM that we already know to be 35. And we have done that by using a legitimate mathematical method. Now we need to divide 11.1 by 0.01. We may take any of a few approaches to the solution of this problem. However, the one that I will opt for is consider that 0.01 is equal to 1 over 100. So we are going to begin by considering that this 0.01 is actually 1 divided by 100. Dividing a number by a fraction is the same as multiplying by the reciprocal of that fraction. Another name for reciprocal is the multiplicative inverse. Dividing a number by 1 results in the same number, so instead of having 100 divided by 1, we will just have 100 right there. Multiplying a number by 100 increases its value by 2 places of decimal. There is only 1 place of decimal. An additional 0 will be included. So there we have it. We only have 1 place of decimal right here. We need to increase this by 2 places of decimal. Therefore, an additional 0 is necessary. The correct answer is option D. We may consider that a number that has a decimal fraction as a reservoir of possible zeros that may be placed to the right of the rightmost non-zero digit without changing the value of the number. In this particular case, we need only 1. So here, we are thinking that this 11.1 that we have here also has a reservoir of zeros that may be placed to the right of this digit. To complete the number of decimal places, we need to just include another one because we are increasing by 2 places of decimal, which is multiplying by 100. Right, that the 0 was added or included to the right of this digit without affecting the value of the number. Then, increasing by 2 places of decimal will be more logical. Now, increasing by 2 places of decimal makes a lot more sense. There is another way that we are accustomed to solving the problem that we have learned in primary school. Instead of having like this 11.1 divided by 0.01, we may call that 11.1 over 0.01. When the denominator, which is the divisor, has a decimal fraction, we multiply the divisor by the power of 10 that is required to clear the decimal fraction. The fraction has 2 decimal places. We therefore multiply by 100. The numerator will also be multiplied by 100 in order that the quotient will remain the same. We need to eliminate these 2 decimal places we multiply by 100 here. Cannot do that without multiplying by 100 in the numerator, unless we are not trying to achieve the correct answer. If we are trying to be correct, then we will multiply both by 100. As a matter of fact, we can see that 100 will cancel with 100. That means that we did not actually multiply by anything. But in order that we may adjust the denominator, then we have taken that approach. Multiplying the numerator by 100 increases its value by 2 places of decimal. It has only 1 place of decimal, therefore a 0 will be included. And any number divided by 1 is equal to itself. There we have 1110. The correct answer is option D, as usual. The number 3.14063 correct to 3 decimal places will be written as, there we have 3.14063, 3 decimal places. We are highlighting 3 right there so that we do not forget that we are going to 3 decimal places. Locate the third decimal place, which is 3 digits to the right of the decimal point. 1 decimal place, 2. We are at the third decimal place right there. Check the digit that is next in order of significance, that is the 1 to the right. The digit is a 6, which is greater than 5. We therefore add 1 to 0. And that is the way that we round numbers. So we go to the specified number of decimal places, then we check the other one. If it is 5 or more, we add 1 right here. So we have 0 plus 1 is equal to 1. The other digits are not affected by the operation. They will return just as we have them. The correct answer is option B. Express 0.12 as a fraction in its lowest terms. I like this problem. Decimal fractions are all fractions whose denominators are powers of 10. The number of decimal places tells us the power of 10 concerned. So 1, 2. So we have what? We have 2 places of decimal. Therefore, the power of 10 that we divide by is 2. 10 to the power of 2, which is 100. The number of decimal places is 2. The power of 10 that we divide by is 10 to the power of 2, or 10 squared. The fraction is therefore the equivalent of 12 divided by 100. There we have it. The fraction may be reduced by a common factor of 4. 4 into 100, we get 25, and 4 into 12, we get 3. The correct answer is option B, 3 over 25. On the next slide, we will take a look at a bit of mathematics that could have helped us to arrive at our answer without actually going through so many steps, or at least without giving so much consideration to so many principles. It is not difficult to look at 0.12 and know that it is actually 3 over 25. Let us take a look at how it may be done, then examine the principle behind it. We need to see that 0.12 is actually 3 over 25. Right. What we will do is take a look at how easily this may be achieved, and also consider the principles that are behind it. In dividing a number by 25, we multiply the number by 4, then take 2 decimal places. It's as easy as that. 7 over 25, multiply 7 by 4, we get 28. Making that into 2 decimal places, we get 0.28. 0.28, no problem. That one, multiply 9 by 4, 36. 2 decimal places, 0.36. How nice and easy. 9 multiplied by 4 is 36. Then we make that into 2 decimal places, and we get 0.36. I'm sure that you want more. What about that one? 8 multiplied by 4 is equal to 32. Making that into 2 decimal places, we get 0.32. There we have it. If this seems unbelievable, check your calculator. So if it is too quick for you and you think that it is not legitimate or will not work in every single case, then you may take a go at it on your calculator. Then you will get the correct answer. Based on what we have done so far, it should not be difficult to see that 0.12 is actually 3 over 25. 3 multiplied by 4 is 12. Making that into decimal places, we get 0.12. One who is familiar with the process has no difficulty seeing it in reverse. If that can be done, then the problem may be solved in a matter of seconds. 25 multiplied by 100 divided by 4. There is no difficulty multiplying or dividing by 100. 4 should pose a little more difficulty, but not too much, especially that we are simply multiplying by 4. Let us replace 25 with 100 over 4. Instead of having 25 right there, we put 100 over 4. Dividing by a fraction is equivalent to multiplying by its inverse. So instead of having 3 divided by 100 over 4, we have 3 multiplied by 4 over 100. That's not difficult now. We have 3 times 4 is 12, and we are dividing by 100. Reducing by 2 places of decimal. And that is the principle behind it. Convert 25 to 100 divided by 4. And we will see that it is not only magical, it is also logical. This is why in dividing by 25, we may multiply by 4 and include 2 decimal places. And that is done by dividing by 100. Because 25 is actually 100 divided by 4. If we are dividing by 25, we invert that fraction. So we have 3 multiplied by 4. Then we take 2 decimal places. What number, when added to 1 and 1/3, gives 2? We need to know what number may be added to 1 and 1/3 in order that the result is 2. Some candidates will have no problem determining that the correct answer is actually 2/3. This they may be able to do in a matter of seconds. 2/3, just like that. They may argue that there are 3/3 in a whole and we need 2 wholes. there is 1 whole and 1/3. In order to complete the other whole, that is to make it up to 2, because we have 1 whole and 1/3. And in a whole, we have 3/3. So in order to make it up to another whole, we need to add 2/3. So it is saying here, in order to complete the other whole, we need 3/3. This requires an additional 2/3. Good. Others may want to go arithmetically on paper. They will say that a number, say x, is added to 1 and 1/3, and the result is 2. Then write the corresponding equation, like so. So they say, we do not know what number it is, but we need to add a 1 and 1/3 to that, and the result is 2. We may transpose 1 and 1/3, that is, subtract 1 and 1/3 from both sides. 1 and 1/3 will be eliminated from the left hand side, and on the right hand side we will have 2 minus 1 and 1/3, like that. We may write 2 as 2 over 1, that is as a fraction, and write 1 and 1/3 as an improper fraction by saying 3 ones 3 plus 1 is equal to 4. So we have 4/3. That is our problem. The fractions have different denominators. Find the LCM of the denominators. 1 and 3 is 3. So we say now 1 into 3 is 3. 3 times 2 is 6. And on the other hand, we say 3 into 3 is 1. 3 into 3 is 1. 1 multiplied by 4 is 4. So we have a minus 4 right there. Find the difference between the two numbers. 6 minus 4 is equal to 2. We have our 2/3 right there. John, Peter, and Mary shared a sum of money in the ratio 2 to 4 to 9. John and Peter together received $360. How much money in all was shared? John and Peter together received $360. It is plain to see that the ratio has 3 shares. We may also say that the 3 shares constitute 15 units. Of course, we have 2 plus 4 plus 9, and that is equal to 15 units. John and Peter together received $360. Their combined number of units is 2 plus 4, which is equal to 6 units. In order to find the total amount, we need to go from 6 units, which is the number of units that John and Peter received together. So John and Peter receive 6 units. That is the total number of units that they both received. 2 plus 4. This is $360. So we need to go from 6 units, which is $360, through 1 unit to 15 units, because the problem requires that we determine how much money in all was shared, and all represents 15 units. So we need to move from 6 units, which is the amount of John and Peter together. We will move to 1 unit, then to 15 units. Let us make use of the equivalent relationship between 6 units and $360. So we have 6 units there. That is represented by $360. We have the amount of money that is equivalent to 6 units. We may use this to find the equivalence of 1 unit. So here we have 6 units equivalent to $360. Then what do we imagine? 1 unit is equivalent to 360 divided by 6 is equal to 60. 1 unit is $60. The total number of money is equivalent to 15 units, as we have discovered right here. We have the amount equivalent to 1 unit. All we need to do is multiply that by 15. So 1 unit, which is $60, multiplied by 15 will give, of course, 15 multiplied by 6 is 90. Multiplied by 60 will be $900. So there we have $900, and that is represented by option D. Many candidates will have no difficulty seeing the 2 steps that are necessary in solving and may take them in one. So instead of taking 2 individual steps, they just do that. Divide by 6, then multiply by 15 in 1 step, and there they will have their answer in a matter of 0.5 seconds. The first 3 common multiples of 3, 4, and 6, that is what we are attempting to determine, or to see which one of these options will represent the first 3 common multiples of 3, 4, and 6. Examiners seem to expect that students will confuse factors and multiples. But even worse than what we expect is the inclusion of 0 in option A. 0 is not usually listed in a set of factors. The factors of a number, say x, are those numbers that will divide into x without a remainder. Option A is automatically out because it has 0. 0 is not usually listed in the set of factors of a number. 0 is not usually included in the set of factors of a number because of, probably among other reasons, when it is divided into another number, the quotient does not exist. That means it is a large number, so large that it really does not exist. By definition, the result is called infinity, and it is written like this, like an 8 laid down on its side. The factors are not what we want on this occasion. We need the multiples. Further, we need common multiples. That is, each multiple must be a multiple of 3, it must be a multiple of 4, it must also be a multiple of 6. According to the statement of the problem, we need the first 3 numbers that are multiples of 3, 4, and 6. Those will be the numbers that each of the numbers can divide into without leaving a remainder. Therefore, the numbers that we are talking about, that we need those 3 common multiples of 3, 4, and 6. Each one must be divisible by 3, it must be divisible by 4, and it must also be divisible by 6. We may continue with the process of elimination. The numbers in each option must be numbers that each of 3, 4, and 6 can divide into without leaving a remainder. In B, 3 cannot divide into 4, and in C, 6 cannot divide into 8. Those options are also eliminated. we need in these numbers, each one of these must be divisible by each one of these. For 3, only 3 can go. So we know that this one is not correct. Or we may say 4, and we say 3 cannot go into 4 without leaving a remainder. It is eliminated. Also here, we have 8. 3 cannot go into 8 without leaving a remainder. That one is also eliminated. The correct answer is option D, by elimination. Some candidates will not have any difficulty seeing that option D is correct. Even GSEC candidates will not all have difficulty determining the answer on inspection. However, let us write down multiples of each number and find the first 3 numbers that are multiples of them. So we have, this is the list of the multiples of 3, list of the multiples of 4, which of course not all of them, some of. So a list of some of the multiples of 3, a list of some of the multiples of 4, and a list of some of the multiples of 6. They are given in succession, so we do not have any in between. But surely we have a lot more after that are not mentioned. We will begin by identifying the smallest and continue through the largest. That is, the smallest number that is in each list. That is, the smallest number that is a multiple of 3, it is a multiple of 4, and it is a multiple of 6. The first one is 12. We can identify it right there. And then we go all the way over to 24. Then we will travel, no doubt, all the way over to 36. And see, we have identified every single one of them. We have confirmed that the correct answer is, in fact, option D. This problem requires the application of the distributive law, but not a typical application of it. We need to be aware of the law that states that multiplication is distributive over addition. In the typical application of the law, we are accustomed to seeing a sum being multiplied by a single term or by another sum. For example, we're going to multiply a sum by a single term. So we have D multiplied by A, we get AD, just to put them in alphabetical order. And then we have D multiplied by B, we have BD. And that is the way that we typically apply the distributive law. D is distributed to both terms, as we can see. Good. What makes the problem atypical is that A, the rule is to be applied to numbers rather than symbolic terms like letters. And B, any one of the numbers may be treated as the sum. So in this particular case, as we can see, according to what we have here, we are just working with numbers. That is for the first point. The second point is, because of that, any one of these numbers can be treated as the sum, and the other one may be treated as the number that we are multiplying the sum by. So we may say that 130 is the sum of 130, and that we multiply by 25. Maybe that is the case. This causes the identity of the sum and the multiplier to be indefinite, which causes their determination to be dependent on the manipulation of the candidate. Okay, so let us take a look at what that means. That means we do not know if 25 is the sum or 130 is the sum. And let us say that 130 is the sum. We may use, instead of 100 plus 30, we may use 70 plus 60. All of that is dependent on the manipulation of the candidate. So that kind of causes the problem to be more sophisticated. I am proposing a solution of the problem that is not among the options. Use 130 as the multiplier and 25 as the sum. 25 will be written as 10 plus 15. So we have 130 as the multiplier, and then we have 25 as the sum, 10 plus 15. So we have 130 multiplied by 10. That is what we have there. We will have 130 multiplied by 15. There we have it. 130 multiplied by 15. The answer is not among the options. It was designed that it is not among the options. So the answer is not among the options, but we may use it to come to a conclusion that will help us to identify the answer quite easily. What do we notice? 1. In the answer we expect 2 pairs of brackets separated by the addition sign. That is what we have there. 2 pairs of brackets separated by the addition signs. That's what we have. We also expect that both brackets will contain one of the numbers. So we have, in both brackets, we have 130, which is of course one of the original numbers that we have here. And what do we expect? We expect the other 2 numbers to be the numbers that will add to give the other one. So 25 is the sum of the other 2, while the 30 is present in both brackets. The other 2 numbers in the brackets will be the sum of the other numbers that is in the statement of the problem. That is, the 10 plus the 15 is equal to 25. So we expect 2 pairs of brackets separated by an addition sign. Then we expect one of the original numbers to be present in both brackets. Then we expect the other number to be the sum of these 2. Based on those expectations, we know that the only 2 options that are in the form required are options C and D. Option D is obviously incorrect. Let us take a look at the reason for this. Only the first requirement is met, namely the expression has 2 products in brackets separated by an addition sign. That one is met. What about those 2 numbers? Those 2 identical numbers need to be equal to one of these. That's not the case. So we know that option D is not right, because if we were using the distributive law, then one of these numbers would have been distributed to both brackets. That's not the case, because the number that is distributed in this particular case is 100. So we are sure we are wrong already. The identical numbers are not in the statement of the problem, as we have just mentioned. Then what about those 2? 30 plus 25. Those numbers should actually add to give one of these numbers. It is not the case. The sum of the other numbers in the brackets is not equal to any number that is in the statement of the problem. Therefore, the other 2 counts are wrong. Option D is doubly wrong. Option C is correct. With all of the other options eliminated, the only correct answer is option C. Let us take a look at why it is correct. In option C, all of the requirements are met. The expression has two products in brackets separated by an addition sign. That's right. We must have two products separated by an addition sign. We have that. Then what do we know? The identical numbers are in the statement of the problem. We have the number that is distributed is 25. So we have it right there. 25 must be one of the numbers here. So we can say that this 25 is the one that was distributed, and that is the one that was distributed. Therefore, the other number is representing the sum. We will expect that these two will add to give 130. The sum of the other numbers in the brackets is equal to the other number in the statement of the problem. So we see that we are adding 30 with 100. The result is 130. No one expects us to go at such length in order to solve the problem. This is just a matter of taking a microscopic look at the principles that are involved. So we are just taking a look at the principles involved. Not that we have to go to such an extent. All we need to know, as the principles have proven, is that one of the numbers must be like the number that we are multiplying by and distributed to both brackets, and then the other number will be the sum. So in the brackets we will have the other two numbers will add to give 130. Keep your eyes open and you will realize that the negative sign is not a part of the fraction that is to be cubed. Cubing the fraction will not affect the negative sign. This negative sign that we have right here outside of the bracket, that means we have a half and we are cubing that half, and the cubing of the half is not going to be affected by that sign. Also, if the negative sign were to be included as a part of the expression that is to be cubed, the sign of the factor will not have been affected by it, as the cube of a number will have the same sign as the number. If we cube a number, the answer will have the same sign as a number that we cube. Therefore, if we cube a positive number, the answer is positive. If we cube a negative number, the answer is negative. So this sign right here, if it were placed inside or outside of the brackets, then the result would have been the same. The negative sign will therefore be applied to the cube of the number as follows. The negative sign is left where it was before. Then we cube the half. In cubing a number, we multiply 3 occurrences of that number together, as we are doing right there. The result is negative 1/8. The numerators are multiplied, so we have 1 multiplied by 1 multiplied by 1, and that is 1. And the denominators are multiplied. 2 multiplied by 2 multiplied by 2, and that is equal to 8. The correct answer is option A. The nature of the answer suggests an awareness that candidates will multiply a number by 3 when intending to cube it, and also that they have a problem manipulating signs and powers. Pay special attention to the requirements of the problem. Some of the principles that are involved in manipulating signs and powers are included in Richard James Mathematics Resources. Therefore, by seeing this, we do not need to be alarmed by it. What is the value of the digit 3 in the number 3,241? The value of a digit in a number is dependent on two things. The first one, the value of the digit itself. So the value of a digit in a number is dependent on two things. The value of the digit itself, called the face value of the digit. And the second one, the value that the digit has because of its position relative to the other digits. And that one is called the place value. Let us first place the number in question under the microscope. There we have it, under the microscope. Let us take note of all of the place values of the digits in the number. So we have thousands, hundreds, tens, and ones. The value of a digit in a number is equal to the product of its place value and its face value. Write down the face value first. Of course, that is a 3, so you just write 3 down. Multiply that by the place value of 1,000. So we have 3,000. And that is our answer. The correct answer is option D. And I know that some candidates may be saying, but we did all of this in primary school. Why are we solving these problems at the CXE CSEC level? Some of us do not mind because we want easy so-called. So we want so-called easy problems to solve that we may get the answer in a matter of seconds. The more easy problems we have, the greater our chance of passing. But do not forget that this is mathematics. And your mathematics began when you started to count or identifying digits. So we expect the CXE CSEC to have problems that will take us from when we just started counting up to this stage. Of a class of 32 students, 17 study music and 20 study art. What is the least number of students who study both music and art? What will be the result of adding the numbers? Those that are in the set M who study music and those that are in the set A who study art. We get 17 plus 20 is equal to 37. And that 37 is of a class of 32 students. Notice that the number is greater than the total number of students. Common sense should tell us that some of the students must have been included twice. The number that we have in excess will be the number of those that have been included twice. Included twice means that they belong to both sets. So 37 minus 32 is equal to 5. That is the excess. Those belong to both sets. The correct answer is option B. The set equation for the number of elements in each section of two intersecting sets could have been used in the calculation. On the next slide, we will take a look at it. That is the set equation for the number of elements in each section of two intersecting sets. There we have it. N A union B is equal to NA plus NB plus N A intersection B. That is, the number of elements in the union of both sets will be equal to the number of elements in A alone plus the number of elements in M alone minus the number of elements in the intersection of A and M. There we have the equation. The statement requires us to determine the number who study both music and art. That will be the intersection of the two sets. In the equation, it is the only unknown. Let us substitute the values into the equation. The unknown will be called x. Of course, we know of a class of 32 students, we know that that's the union of the two sets. The total number will be those in the union of the two sets. Then, easily, 17 study music and 20 study art. So, that is equal to 17 plus 20. And finally, the sum of the numbers of those who study each subject we have those already. We do not know the number of those who study both subjects, the intersection of the two sets, and that we will call x. We do not know the number in the intersection of both sets. 32 is equal to, when we add 17 plus 20, 37 minus x. What do? We transpose this 32 to the right hand side. It becomes a negative 32. We transpose this negative x to the left hand side. It becomes a positive x. And x is equal to 37 minus 32. X is equal to 5, as we have determined already. Let us place the information in a Venn diagram in order to clarify the presence of a particular word in the statement of the problem. So we have a particular word in the statement of the problem that we intend to clarify. Let us draw a Venn diagram in which the sets are labeled with the letters that start the name of the subjects. So we have, no doubt, the Venn diagram with the universal set M and A are inside of the universal set, and they have an intersection. Both music and art. When placing numbers in the sets of a Venn diagram, place a number in the intersection of the two sets first. So intersection of the two sets first, we have that right there. Then we have 17 study music. Let us include the number of elements that belong to M only. M has 17 elements, 5 of which are already in the intersection. So we have, notice that these 5 are also in M, and a total of 17 is there, so the rest will go right there. 17 minus 5 is equal to 12. 20 study art. 5 of the 20 elements of A belong to the intersection, just like we have done a second or two ago. So we have 15 will be placed there because in all we have 20, and 5 is already in the intersection. We are taking a look at the word least, why it is placed there in the problem. The word least was included because the possibility exists that there are students in the class that do not study any of the subjects. Let that possible number be represented by n, and we put it right here in the Venn diagram, but not in any of the sets because it is not a part of any of them. In our calculation so far, we have assumed that the value of n is equal to 0. This causes the 32 elements of the universal set to be in the union of the two sets. So we, in our calculation so far, we say that n is equal to 0. We did not include any number at all that is outside of the two sets. Therefore, all 32 elements will be in the union of the sets A and M. Let us say that n is equal to 2. The number in the universal set being the same, the number of elements in the union of the two sets is reduced by 2. So let us say n is equal to 2. We are going to change this to a 2 in a few seconds. The result would have been that the intersection will be increased by 2, and in each of the sets, number unique to each decreased by 2. This result would be the intersection will be increased by 2, and in each of the sets, the number unique to each will decrease by 2. So if n is equal to 2, what will happen here? This one will increase by 2, and each of these will decrease by 2, as we have it right there. Notice that the number in the universal set is preserved, and the number that study each subject is also preserved. Notice that we have what? 10 plus 7, 17. 7 plus 13, 20. And if we add all of these, we get 7 plus 13 is 20, plus 10 is 30, plus 2 is 32. So the number present in the universal set is preserved. This is why some examiners include the statement that each student studies at least one of the subjects. They know that if there are some who do not study any of the subjects, that would imply an increase in the number of those who study both. So most times we have, along with this, we may have a problem like this. Of a class of 32 students, 17 study music and 20 study art. What is the least number of students who study both music and art? If each student studies at least one of the subjects. So by including that statement, what will happen? We will not include any here, because each student studies at least one of the subjects. We know that we do not have anybody in the universal set that is not a part of the two sets that we have inside the universal set. Because if we kind of leave that option open, we know that if we have a number, as we have right here, that is not studying any of the subjects, that number will increase the number that study both and will reduce each of the numbers that are unique to each set. In which of the Venn diagrams is the region A intersection B complement shaded? We need a region where A intersects with B complement. That region represents the common element of A and B complement. B complement is a set of elements that are not in B. We therefore need the region that is shared between the set A and the set of those elements that are not in B. So we need those that are shared between the set A and the set of those elements that do not belong to B. The intersection, common elements of A and B complement. So we have the set A. We know that this one is the correct answer. Let us use it. All of the elements that are unique to A. That is the answer that we have received. But how do we determine that? We need to consider all of the elements that are in A. Consider all of the elements that are in A. Then we need to consider all of the elements that are not in B. Those that are not in B, this we have B right here. All of the elements that are not in B. What do the two sets have in common? Those that are in A along with those that are not in B. And we are sure that this shaded region is what that represents. The correct answer is option C. Some candidates may not be able to solve the problem at sight. On the next slide, we will take a look at how we may be able to use a diagram and solve the problem in a more logical way. Let us draw a Venn diagram with two intersecting sets and only one element in each region. So we have two intersecting sets and we have one element in each region. That is, we have one element unique to A, one in the intersection, one unique to B, and one that is not in any of the sets but inside of the Venn diagram nonetheless. Let us write down the elements of A. 4, 2. Write down the elements of B complement. Those that are not in B. Those that are not in B are 4 and 1. The only element that is common to both sets is 4, because we need the intersection of A with B complement. We need the common element of A and B complement, and that element is 4. The entire region that contains 4 represents A intersection B complement. It is the one that is shaded in option C. So we have written down, since we need A intersection B complement, we have written down A right here. We have written down B complement right here. Then we have found the intersection of the two, the common elements. In this particular case, it's a single one, 4. The region that contains 4, this region is the answer that we are looking for, and there we have it. It was not necessary to place more than a single element in each section. The elements are identifying the sections and making sure that every single region is represented. So we are not writing down a lot of elements because we are just identifying each unique section of the Venn diagram. And that is enough to determine our answer. In the Venn diagram, the shaded region, we need to know what it represents. Sometimes it is a bit more challenging to look at the situation from the perspective of the shaded region. It may be easier to identify the region that is not shaded. Only set P is not shaded. The shaded region is the entire part of the Venn diagram that is outside of P. This represents the complement of P, which is P complement. Option A is correct. The complement of a set, say P, is called P complement and is written like this, with an accent like we're doing a foreign language, or with a superscript that is a slash. It is a set of all elements that are not inside of P. The other options are for those candidates that are too advanced for CSEC. Some expect a difficult problem and think that they need to go around the wall of Jericho 7 times in order to arrive at the correct answer. When solving a problem, always look for the simpler or the simplest way out. If U is the set 1, 3, 5, 6, 8 and A the set 3, 6, then the number of elements in A complement is what we are determining, not A complement, the number of elements inside of A complement. Let us construct a Venn diagram that represents the information. The set A will be contained in the universal set. The element of A that are in the universal set will be placed in the set A. Where else? So these are the elements that are in A. 3, 6, they are placed inside of A. The remaining elements of U are placed inside of the Venn diagram, but not in the set A. They are placed in the Venn diagram. They are 1, 5, and 8. The elements of A complement are elements that are not in A. That is, those that are in the Venn diagram, but they are outside of A. And there we have them. A complement is equal to 1, 5, 8. That is the set A complement. We have the elements of A complement, but this does not satisfy the requirements of the problem. The number of elements thereof is what is required. The number of elements is 3. The correct answer is option B, 3 elements. After identifying the elements of A that are in the universal set, we may say that the rest do not belong to A and therefore constitute A complement. So there we have all the elements that are in A. The rest are a part of A complement, therefore. The number of elements that remain is 3. We have them right there in red. So option B is correct, 3 elements. The number of elements that are in A complement is therefore 3. The correct answer is option B, as we have determined on a previous occasion. A woman buys a pair of shoes at a sale. She pays $60, saving $15 on the normal price. The percentage discount on the shoes is what we are trying to determine. What is the percentage discount? The problem seems to be fairly easy and straightforward. However, there are some vital bits of details that, if missed, may result in a candidate making a meal of it. The $15 was saved on the normal price. This means that the normal price was $15 greater than the present price. Let us find the normal price. She paid this, saving this. That means the normal price was greater because she's saving now, and she's saving 15. So that is it. 60 plus 15, $75. What may be a bit elusive is a number that it should represent a percentage of. In buying or selling, the percentage is usually given relative to the original price. In this particular case, the price before the discount was calculated as $75. Let us find the percentage of 75 that 15 represents. So find the percentage of 75 that 15 represents. 15 over 75 multiplied by 100. We can already see that 15 is 1/5 of 75, making the percentage, we know that the percentage associated with 1/5 is 20%, so the percentage is 20. Let us reduce the fraction by a common factor of 25. 25 into 75 is 3, into 100 is 4. Then reduce a common factor of 3. So we will reduce by a further common factor of 3. 3 into 3 is 1. 3 into 15 is 5. 5 multiplied by 4 is equal to 20. The correct answer is option A. If a mistake were made and the percentage was calculated relative to the selling price, which is $60, that would have resulted in 25%, the answer of option B. Be always mindful that the percentages are relative to the cost price unless otherwise stated.